This video demonstrates the intuition of F-tests, including the one-way ANOVA F-test and the global F-test in the multi-regression problems. It's intended for students who have already worked through some of the technical details of these tests, that is the calculation of the ANOVA table for the one-way test or for the regression example. And it's going to demonstrate just the intuition of what the F-statistic is doing and what that test represents and what a large value of the F-statistic means. To show this intuition, we've got a sample data set here that's representing real estate prices. So we've got the sales price of, I think it's about 15 houses. I have a second categorical variable or qualitative variable that is the name of the seller, the realtor who sold the house. Think of them as Andy, Bob, and Chris, or person A, B, and C. And then a third variable that is the number of weeks that the realtor and the homeowner were in a relationship before they put the house on the market. And presumably houses that wait longer before they go on the market means the realtor has more time to make suggestions about, say, kitchen upgrades or how to stage the house before it goes up for sale. Now for the one-way ANOVA test, we're only going to look at the first column for now. That is the sales price. And a graph of the data might look something like this. So on the x-axis here, the vertical axis, we have sales prices. The sample mean of about 486,000 is this orange line right here. And then all of these blue dots represent houses. The thing on the x-axis here is it's just the numbers 1 through 14 or 1 through 15. And those correspond to the location of the house in the data set. So they really have no meaning. It doesn't mean that the one over here is somehow more or somehow different than the one over here. Now when we complete the ANOVA table, one of the things that we're calculating is how much variation there is in the data set. So for this first observation here, we've got a house that's sold for about $760,000 or so. And that's considerably above this sample mean of 486. And if we look at that difference between 770 or so and 486, that represents the height or the length of this line. And if you square that, you get one component of what's called the sum of squares total. It's measuring the total variation from the mean of these data points of 486. So we calculate those differences, or the length of those lines, for every observation, square each one, add them all up, and we get this thing called sum of squares total, or sometimes called total sum of squares. And it's the sum of all of those squared differences. Now it might be interesting instead to look at which seller or which realtor was selling the house. So we have these observations or these points now color-coded. Observations 1, 2, and 4 all correspond to seller A. Seller B is all of these red points. Seller C is all of the black points. And we see that the mean of the green points is considerably higher than 486,000. The mean of the red points is considerably below it, and the mean of the black points is a little bit above it again. Well, that means that if we look at the difference between, say, this $770,000 house from the sample mean of 486, you're going to get a much larger difference than if you look at the deviation of the difference between 770 and the mean of just seller A's houses. That means that if you wanted to make a prediction about the selling value of a house, if you know nothing else about the house or the seller, you would guess that it would sell for something like 486,000. However, if you knew that that house was being sold by seller A, you might make a slightly higher guess, and on average your guess would be likely to be better. The question in an ANOVA analysis is whether those predictions improve slightly or whether they improve substantially. Now to examine whether or not they improve substantially, look at these improved guesses. So for the greenhouse, now we're going to guess that the house would sell for $600,000 instead of $486. And we see that the deviation, instead of being this length right here all the way up and all the way down to 486, that deviation is quite a bit smaller. This deviation ended up being a little bit bigger. This one went down to almost 0. You can kind of see the difference here. In very light gray here, I have the line for 486 drawn. And we see this dotted line right here is the difference from the overall mean, called sum of squares total. And this thing right here is called sum of squared error. That is, it's the rest of the differences that you weren't able to explain after you made your best effort. Now, the calculation of the F-statistic says look at not sum of squares total, but what's called sum of squares treatment. And that's the amount of error that you were able to explain. It's the total squared differences minus the error that remained after looking at treatment means. Sum of squares treatment divided by the number of treatments minus 1 kind of gives you a measure of how much was explained per treatment. And then sum of squared error divided by roughly the number of data points that you have minus the number of treatments, and minus k. If these sample means or these treatment means here did a really good job of improving your predictions, then your treatments will have explained a lot, and this top of the fraction is going to be large. Relative to the amount of error that's left unexplained, this will be small. Large value divided by a small value is going to get a large value of your F-statistic, presumably larger than a critical value, and that will indicate that looking at treatment means instead of the overall mean gives you a significant improvement to your predictions. Now, the global F-test in multi-regression is doing something very, very similar. It's just that it's using a regression function instead of a single variable such as housing prices. Now, when I illustrate this, we're going to have to do it on a two-dimensional plane because I can't show a three-dimensional graph in a PowerPoint slide. But the calculation using all of these SSR and SSEs down here is exactly the same if you have multiple x variables instead of only one. In the global F-test, the null hypothesis is technically written as all slopes being 0, but intuitively it's saying that the regression predictions aren't any different than making predictions with the mean of y. This is very similar to what we did in the one-way ANOVA test, where you'd make predictions for housing prices as being 486,000 across the board. The alternative hypothesis is that using the regression line does improve your predictions somehow because there's important information in the x variables. That's the exact same as using the treatment means to make better predictions because there's some information there, such as which seller is selling the house. The calculation in the F-test, there's a couple of symbols that are different. Here we've got k on the bottom of the top of the fraction instead of k minus 1. This is n minus k minus 1 instead of n minus k. We have this thing here called sum of squared errors. This is called sum of squared regression instead of sum of squares treatment. Generally, though, what we're looking for is exactly the same. If the top of the fraction is large, the bottom of the fraction is small, that's what's going to result in a large value of the F-statistic, and it would cause you to reject the null hypothesis. Now, graphically, here is the same data on housing prices, although here we have a much more meaningful variable on the x-axis. This is the number of weeks before the house went on the market. And we can see here we definitely have an upward sloping trend, and that should cause us to reject the null hypothesis that the regression line is useless and does not offer any improvement. Now, if we ignored the regression line and we just tried to make predictions, our best guess for the selling price of a house would be $486,000. And all of these blue lines here represent how much you miss. The exact same principle as in the ANOVA test, although the data points have been sorted a little bit differently. Again, you calculate the difference between the actual value minus your prediction using just y bar, or the sample mean. Square all those differences, and we get something that we still call sum of squares total. If instead we use a regression line to make predictions, Say if a house is on the market, if it's on the market after the realtor and the homeowner know each other for 2 weeks and they try to prep the house a little bit, then you might predict that the house is going to sell for, give or take, about $440,000, whatever that line says. And if the realtor and the homeowner know each other for maybe 7 weeks, a regression line predicts that that house is going to sell for about $630,000. Now, if we used those to make our predictions instead of the sample mean of 486, we see that a lot of these differences are considerably smaller. If we take those differences and square them, we get what we still called sum of squared errors. That's your differences after doing as well as you can at making really good predictions. And the difference between your sum of squares total and your sum of squared error, just with a simple subtraction problem, in the ANOVA case we call that sum of squares treatment, and in the regression case we call that sum of squared regression. And then your calculation of your F-statistic, sum of squared regression divided by k minus 1, where k is the number of explanatory, it's the number of slopes, the number of parameters that you use in the regression function. So here we estimated a slope and an intercept. K minus 1 then is going to give you the number of slopes. That'll be 1, because we have one x variable. And then on the bottom, we have sum of squared errors divided by roughly the number of data points that you have after you subtract the number of variables that you used. Again, we have the same intuition as with the ANOVA F-statistic. SSR over k minus 1 is roughly a measure of how powerful the regression is, or how much the regression was able to explain, relative to the amount of error that was left unexplained. And again, if the regression explained a lot, the top of the fraction is going to be large. There's going to be relatively little error remaining, and so the bottom of the fraction is going to be small. And that's precisely what is going to give you a large value of an F-statistic. So a big value of F means SSR is large, SSE is small, and the regression was successful at making much better predictions.